In this video, we're going to be solving a Newton's law problem that involves kinematics equations as well. So let's read the problem before we try and solve it. A 65.5 kilogram skateboarder pushes off a wall with a force of 109 newtons backward. The push lasts for 0.487 seconds, and the force of friction on the skateboarder has a magnitude of 48 newtons. How far away from the wall will the skateboarder come to rest? This question it's a very interesting question in that you have to remember there's two parts to it. There's going to be the part where the skateboarder is pushing, and there's going to be the part where the skateboarder is no longer pushing but still has a force of friction slowing them down. So it will start at rest and end at rest, but we're going to have to solve it as two entities. Like I said, part one will be where they're pushing, part two will be where they are slowing down, and we will add the two distances together. So the first thing I do is I reread the question and I write down any relevant information. So a 65.5 kilogram skateboarder, again, it's the second time through, so we know the mass is 65.5 kilograms. Pushes off a wall with a force of 109 newtons backward. We're going to say that's the applied force, but I'm not going to add in the direction yet. And you'll see why in just a moment. The push lasts for 0.487 seconds, so we know delta T. And the force of friction on the skateboarder has a magnitude. So again, the force of friction, we only know the magnitude. We'll need to sort out direction in just a second of 48 newtons. How far away from the wall will the skateboarder come to rest? So we want to know delta D total. Now, like I said, delta D total is going to be made up of delta D while pushing and delta D after the push. So we're going to need to solve for those. The first thing I do is to help me sort out these directions, I want to do a system diagram. So I'll write some reference coordinates. Up, we'll assume is the positive y, and forward, we'll assume is the positive x. So I add a system diagram in. So I have a wall, and I have a skateboarder here. I'll just draw them as a box. They are going to push on the wall. Well, we can assume the wall will not move. So if the wall's not going to move, then the skateboarder is going to feel the push pushing them forward, just by Newton's third law. I push on the wall pushes back at me with an equal force but opposite magnitude. So we're going to say F applied actually pushes them forward, because again, they're pushing this way, so the wall will push them back. The wall's not likely to move. The skateboarder, being on a skateboard, would have relatively low friction and therefore should move forward. At the same time, friction will oppose that motion, so friction should be pointing backwards. Now, we obviously have gravity acting on the skateboarder, and we can assume the surface to be level because we weren't told anything else, so you'd have a normal force of equal magnitude, thus canceling out the gravity. So after doing this, I can add in a direction forward to the 109, which flips it from what the question said backward, because they push, but now the wall is the thing acting on the skateboarder. And again, when we come to the free body diagram, we can only include forces that act on an object, not forces it's exerting on other things. And the force of friction will be backward. Well, as we like to sort out directions early in a problem, forward and backward we won't be able to work with, so we quickly change this to 48 newtons negative forward. Now I will draw a free body diagram for this, or the skateboard. So the free body diagram, we draw just the skateboarder, who would have gravity acting on them, and the normal. And again, just like we said before, those will cancel out. We would have an applied force, the feeling of the wall pushing back, that's the third law reaction, and they will experience a force of friction opposing their motion. Well, now, like I said, I'm going to divide the question up into two situations. One, while they were pushing, and the second, after the push. So we're going to do while pushing first. And I should include that this free body diagram here is for while pushing. It was just coming off the wall. So we know the V initial in this case is 0 meters per second, or we know we can make that assumption. We know F applied, we know force of friction. We want to know the delta D, the distance covered while pushing. I put a little subscript of WP to remind me of that. And I think to do that, I'll need to solve for the acceleration while pushing. Okay, so quickly I look at my free body diagram, and I can say that the net force on the skateboarder while pushing is equal to the force applied plus the force of friction. And now I can drop the vector signs. We've taken care of direction, start filling in some numbers. So F applied is 109 plus negative 48. At the same time, net force by Newton's second law is equal to the mass times the acceleration. So I can put mass times the acceleration. Again, I've dropped the vector sign. That means any direction I get will be in the forward direction, so I've made that assumption. So the mass was 65.5, and 109 minus 48 is 61. So A equals 61 over 65.5. And again, this was in newtons. Newtons divided by kilogram gives us meter per second squared, which is the unit of acceleration. So we will get the acceleration as 0.931 meters per second squared. Now, that is a positive number. I can include a direction if I want. That means I'm going to get it in forward. Had it been negative, it would still be forward because that's what I was working with. So the skateboarder is accelerating forward at 0.931 meters per second squared. Well, from that, I want to find the distance traveled while pushing. So I'm going to use the formula V initial delta t plus 1/2 A delta t squared. Distance while pushing is what I'm looking for. V initial is 0 times 0.487. I fill in for the time so you know how long you're pushing for. Plus 1/2. And A we just found out is 0.931, 0.487. Sorry, it's a little squished. Squared. I then put that through my calculator, and I get 0.110 meters. So they covered about 0.11 or 11 centimeters while pushing. Now we will need to know the speed they were going at the end too, because the speed they ended up going here is our initial speed when they stopped pushing. So I quickly solve VI, or VF equals VI plus A delta T. I fill in VF equals 0 plus A, which is 0.931, 0.487, and I get the V final as 453 meters per second. Again, because they will speed up as they push, that will result in this V final, 0.453, being the initial after they stop pushing. So I'll just move this forward. So we have that. And now we're going to talk about after the push. And that will denote a subscript AP. So we know after the push, well, we know the V initial is that 0.453 meters per second. We know they're going to come to rest, so V final is 0 meters per second. We know, that's what we know. Now, we can draw a quick free body diagram for this one. And the free body diagram will show us that you still have a force of gravity acting on the skater. you still have a normal force, but there's no more applied force. There's only a force of friction. Well, from that free body diagram, I can then say F net after push equals F applied plus force of friction. Well, we know the F applied is 0, so that's gone. So we're left with F net equals force of friction. Now, force of friction, we're still going to assume forward is the positive direction because I can assume they're moving forward. So this will be negative 48 newtons still. And this, by Newton's second law, will be mass times the acceleration after the push. Okay, and I fill that in, 65.5. Now I'll take 48 divided by 65.5. It'll be newtons divided by kilograms, which will result in meters per second squared, which is the unit of acceleration. And we will get the acceleration is negative 0.733. Well, we expected a negative because they'll slow down whenever they are moving, stop pushing forward. Because the only force acting on them is the force of friction. So the acceleration is going to be in the negative direction. Now that I have that, I can quickly solve for the distance after the push. So I'm going to say V final squared equals V initial squared plus 2A delta D after the push. Well, V final is going to be 0. V initial, we take that final from the last part, we do a bit of math, and we will end up, I'm going to square that, I'll bring it over, so I'll make it negative, and it'll be 0.2052, keeping an extra digit, and negative 1.466 times the distance after the push. I divide that out, and I end up with 0.172, so I went 0.2052 divided by negative 1.466. They're both negative, so the negatives cancel. Meters as our distance after the push. Now, to finish the question, all I do is I say the total distance covered will be the distance while pushing plus the distance after the push. So I quickly get the distance while pushing was 0.110 plus 0.172, and I add those together, and I get 0.282 meters is the distance covered. I could write a statement, therefore the distance covered would be, I don't really have room on the board, so I'll finish up there. So again, feel free to pause the video at any point, go back, and try working through this question with a bit of help.